think they're all these extra houses.
So that's,
I've been there.
all right. So let's see. Since I want to make sure I have time for you to ask questions, because we're only going to get to hopefully what we need for the final part of the assignment today. So the homework will be due on midnight on Friday, okay? And then don't forget we have the abstracts due for your final project on the week on the, yeah.
So there's no notes on problems at 10.
I haven't assigned problems
Okay.
yet, yeah, but, because we haven't gotten to anything yet about problems at 10, but I'll be due the week, Tuesday before Tuesday. Very good. All right, so what we're talking about now is really kind of the heart of quantum optics, at least in some definition of what quantum optics is. As when we introduced at the very first lecture, I said the subject of quantum optics was about coherence. And coherence by and in electromagnetic fields. That's how I'm broadly defining the subject matter of quantum optics. For the first half of the semester, we talked about how electromagnetic fields can drive coherence in matter, create superposition. So coherence, again, was the way I define coherence is the capacity for a system to exhibit interference, okay? And interference, when we talk about quantum coherence, what we mean is interference of probability amplitudes, okay? And so when in the first half of the semester, when we talked about things like Rabi oscillations, we were talking about how when we drive a system with a field that has a well-defined electric field with oscillating with some frequency, we can drive coherence, say we can create superpositions, coherent superpositions, say between a ground state and an excited state. We could rotate on the Bloch sphere into the equator and we created coherence, and that coherence was seen in the off-diagonal matrix elements of the density matrix, right? So we studied all of that. So that's quantum coherence in the matter that was created by field. What we're studying at the moment is quantum coherence in the field, and it's a little bit of a tricky business. It's kind of a lot of tricky business. For all these years that I have taught this course, I have frankly struggled with what's the best way to distill down this into a digestible chunks, because it's somewhat complicated. There's so many different elements of it. So I'll do my best. We'll see how I really struggle with this. I've taught this a jillion times, maybe 10. What did I want to say? So what we're talking about here, when we talk about coherence, we're talking about quantum interference in the field. But there's sort of what's a little bit interesting and different in the context of what we're talking about with the atoms is now there's coherence that we think about at the classical level, because we can think about coherence of the classical electromagnetic field, and that's, statistical optics, things we care about if we're thinking about optics and we're thinking about what does it mean to have a coherent source, have an incoherent source. We think about that from the point of view of classical wave optics. And then there's coherence at the quantum level associated with the photons or some aspect of superpositions of the quantum field. And the relationships between them are subtle, okay? And so that's what we're studying at the moment. That's the background, that's the idea. We want to think about this idea about coherence, interference, and its relationship to what we call what are correlations. And it's really the story of waves and particles. This is wave-particle duality on steroids, okay? We learned about quantum mechanics from the beginning, the way it was developed, it was thinking about wave-particle duality. That was a phenomenology that awoke people to the ideas of quantum mechanics. And now we're sort of coming back to the beginning and revisiting this now in the rigorous context of quantum optics with quantum field theory now under our belts. Okay. All right, so, very good. So, what we talked about briefly, or we talked about last lecture, was the notion of the coherence time associated with, an electromagnetic wave like a light source. If we say it has a certain coherence time, if we multiply it by c, we call it that the coherence length of the field. And what that is telling us is the time scale over which the system has a well-defined phase. And what that means is the time scale over which we expect to see interference in a correlation. If we looked at the field and looked at an interference with itself at two different times, there's a time scale over which we would see interference and a time scale over which we wouldn't, because the phase is washed out, okay? And so the way that's natural to measure that coherence time is in an interferometer, because that's how you can look at an autocorrelation of the field amplitude with itself. And so if we look at, we just like to draw non-linear interferometers, not necessarily, maybe we use a Michelson or something that's easier to align, I don't really care. But the point is, it's just conceptually, what we're saying is here that we have our field is defined by some complex amplitude at this interfield, which is a random variable. Generally, it's fluctuating in some way. And the output field over here is a superposition. There's no reason not to put a little tilde on top because I'm not doing vectors. So give it a hat rather than shoes. The complex amplitude over here is related to the complex amplitude at the input at the retarded times, where I have two different paths, L1 and L2, and T1 is the retarded time. So what I see over here is a superposition of those two electric fields, one that goes along this path and one that goes along that path. With the beam splitters, we get path, right? And so the output intensity, well, this is a random variable, and so the output intensity, I need to average the intensity over the probability distribution, which in an ergodic system, I'll put a sub C. This is the classical average. I'm integrating over the probability distribution of the intensity here, the output intensity. So I have some probability distribution, and what we found was that this was equal to, and we did all the rigmarole, and we thought about, for the particular case that we have stationary statistics and ergodic system and the statistical assumptions that are true of things like thermal sources, incoherent sources, that this was equal to 1/2 the input intensity plus the real part of a correlation function. So this gave us that autocorrelation function that we were talking about just at the beginning. I'm correlating the field with itself, where tau is the time difference. Okay, it's the path length difference over C. And the time scale over which this is well correlated gives me the coherence time. And for a collision broadened source that has a Lorentzian line width, this falls off exponentially with time. So this correlation function we call the first order correlation, is correlating the field with itself. That's a first order correlation. And for this case, this was equal to the input intensity times e to the minus I omega t, and it fell off with some time scale tau sub c, which is the correlation time. And that would show us on an interferometer, if we looked at the this output intensity as a function of tau, we would see interference fringes that would decay. The visibility, as we say, of the fringes, which is how deep, how much, what's the difference between the maximum intensity and the minimum intensity, that visibility would decay as I made the path length bigger and bigger and bigger, and eventually I would see no interference at all. Half the intensity would come out this port, and the other half would go out, and that would be the case in which the field is not interfering with itself anymore because the path length difference is bigger than the coherence length. Okay? All clear?
What is the subscript C for the?
Here, this is the. Oh, over here. I just wanted to say that this is the classical. This is the expected value with respect to a classical probability distribution. That's what I'm trying to say. The reason is the bar, we sometimes use the bar on top, but that's the time average. Yeah. Yeah.
So the second term there effectively characterizes the specifically quantum interference effects.
Well, I wouldn't say this has anything to do with quantum interference. This is classical wave interference.
Oh,
Okay, so these are waves. We're not talking about quantum mechanics yet. Here, this is really about the fact that I have a wave that, if I looked at it of some particular realization at some time, would oscillate, and then the phase would jump, and then, you know, the phase would jump again, and because of that, if I looked at the autocorrelation of this with itself times average, I would see this effect. So this is classical wave interference, but with statistical uncertainty in the wave, right? So that's what this means. Now, as we discussed, the famous Hanbury-Brown twist delicious cocktails, Hanbury-Brown twist experiment of the mid-1950s said, well, you know, it's going to be hard to make a balanced interferometer. I'm just going to make things life simpler, and instead of trying to correlate the amplitude of the electric field with itself, I'm going to correlate the intensity with itself at two different times. Do a intensity correlation by just having one beam splitter and a delay line and a square law detector on each port, and then just multiply them together, and I have my input intensity here, and what I see here is the autocorrelation of the intensity with itself at two different times, as opposed to the complex amplitude. Okay, this is the input intensity. That's what this thing is measuring. Okay, and so that's equal to, you know, the square of the complex amplitude with itself at two different times. This correlation function we call G2 of tau. It's a second order correlation as opposed to the first order correlation. And in particular, when we have, so this, you know, is E in star tau, E in tau, E in tilde at 0, E in tilde at 0. That's what that correlation function is, right? It now has 4 amplitudes through the stars, okay? Mandel called this the fourth order correlation, but no, it's G2, sorry. No. So anyway, so what I argued last time without detailed proof is that for the specific case that we had a collision broadened source where the wave amplitude probability distribution was Gaussian, as we have studied for the case of thinking about the random walk and all of that. When we have a Gaussian distribution, this thing, using Wick's theorem, we can write in terms of the products of the correlation functions, and in fact it's equal to followed for the specific case of collision broadening. Where we had a Gaussian probability distribution. Okay? I didn't prove it in detail. You just have to take my word for it. If you want, I'll give you that homework problem. I've done it in the past. All right. And what we see here, oh, sorry, this is a pardon me. What I mean to say is that the 4-point correlation function factorizes into products of 2-point correlation functions. And that's true for Gaussians, because for Gaussians, everything is determined by the 2-point correlation functions, okay? And this is the formula. And this is then equal to u of the intensity at I times the intensity at 0 plus the magnitude of G1 of tau squared, right? And this actually is equal for a stationary source. This is independent of the origin, so that's actually just I0 squared. And this is what we had over here. This is I0 squared times e to the minus 2 times tau over tau c. Importantly, what we see here is that this 2-point correlation function having to do with how the field amplitude overlaps with itself appears in this intensity correlation function, and we can thus, in principle, we can't in practice because we never have detectors that are fast enough to do it, so no one ever does it this way, to my understanding. But in principle, we could, and there were some experiments that showed the signatures of this. We can measure this correlation time that's associated with the wave interference by correlating the intensities rather than the amplitudes. And so if I looked at, so this was related to G1, that envelope is there. What we have in G2 is something that looks darn similar, okay? Where at 0, this is equal to twice the input intensity, or I'll just call it squared, right? When tau is 0, it's twice that. And out here, it's that. So when tau is big enough, big compared to the correlation time, which it falls off like that, this thing factorizes, which is to say, when tau is big enough, the intensity is not correlated with itself. And so the mean of the product is equal to the product of the means. That's what it means to say there's no correlation. But when the time is small enough, it is correlated with itself. And what this is saying, we remember that the mean of the intensity to the power n is like n factorial times that. This represents, if I look, this factor of 2 is the excess intensity fluctuation. The fact that the intensity, if the intensity was constant and wasn't changing at all over all times, then this would always equal this. It would just be the product of the intensities. The fact that it's higher here is a manifestation of the fact that the intensity is fluctuating and is not a constant. Okay. So we can measure the coherence time by measuring the intensity fluctuations. Okay. But that sounds great. That sounds easier. The point really is that this now led to a kind of paradox, because although, coming back to your question earlier, Benny, about quantum, so while I said that this was just wave interference, we could also understand from the point of wave-particle duality, we can understand this from a photon by photon detection. I'll come back to this in just a moment, but if I think about my detector here, I can think about it as detecting photon by photon per photon. If I collect many of those photons, I'll see this classical interference pattern. And the way we reconcile the fact that there are discrete counts with the fact that there's interference is that where the particle is going to appear is determined by its wave function. And the wave function is the electric field. The wave function of the photon is E tilde with proper normalization. And so how the classical wave interferes with itself is equivalent to saying how the photon interferes with itself. Which is to say, there is in this interferometer, a photon might go this way, it might go that way, and where the photon is going to appear, whether it appears in this output port or this output port, is determined by wave interference of the wave function, which is the exact equivalent interference of the classical wave. So the way the wave function interferes is the same wave interference. So we see the same pattern, but the pattern in this case is saying something about the probability, the fraction of photons that appear in this port or the other port. So, and Dirac, when was in the 1920s, when people were trying to understand how do I reconcile wave-particle duality, is the fact that all the photons come out this port versus that port is some collective effect, and somehow the photons are bunching together. He said, no. In an interferometer, each photon only interferes with itself. There is not a collective effect of multiphotons. And that one line in Dirac's 1929 book, which I meant to bring in, caused people to have conniptions when Harry Brown Twist did their experiment. Said, how is this possible? Because in this experiment, no one photon goes two different ways. Either a photon goes that way, there's another photon that might go that way, but this is related to photon coincidence counting. And it's antithetical to the idea of how do we understand this? People said this can't be right because this is related, the coherence is related to interference, and what the heck is interfering here? The photon is not interfering with itself. Now, we'll come back to this. We totally understand this now or after 100 years, not quite 95. 96. My final offer. And I'll explain. It's not, but it's a two-photon interference experiment. Okay, and this opened the door to the whole notion of thinking about many-body interference, in particular two-photon interference, which set the whole stage about thinking about things like Bell's inequalities and entanglement correlation. It really started here. Okay, so I want to make this all a little bit more formal. Let's just think about how we want to describe the fully quantum theory of photon detection, okay? And that's what Glauber did. He said, look, if I'm going to answer the problem, just do quantum electrodynamics. Just write down the quantum field theory. Don't make the semi-classical approximation. Write down the theory of photon detection, where now we quantize the field. And in our simple model, what we can say, we think about it as one atom doing a photoionization, as we've discussed now many times, and I wrote right down again with some interaction Hamiltonian in the interaction picture, which is my dipole interaction, where I have the absorption at some position at time t, and then the emission. So this is the thing that takes me from the ground state to the excited state. And this is the thing that gives me emission, that takes me back to the excited state, to the ground state from the excited state, and that's involved the negative frequency component. So we will remember that E plus, the positive frequency component, has the annihilation operators. So this term says I annihilate photons, and in the process, I go from the ground state to the excited state. In this case, I create photons, as say photons are emitted from the atom, and I go from the excited state to the ground state. So this part is associated with absorption, and this part is associated with emission, and I've written things in the rotating wave approximation. And if you do the rigmarole of Fermi's golden rule and the like, where I have some initial state, so my rate of absorption, which is associated with a single photon, a single photoelectron emission, that is associated with the absorption of a photon. What I have is my initial state. I'm in the ground state. I have some initial state of the field. I have my interaction Hamiltonian in the interaction picture, and I just take the absorption term of that. I'm going to call this the positive frequency part. That's the part that goes here. And then I go to the excited state with some final state of the field squared, okay? But I'm not interested, I'm not going to measure what the field is after. I'm just going to measure the electron. So my total rate is irrespective of what the final state is, and I sum over all final states of the field. Sometimes we say we trace out. That term tracing will come back here, okay? So if I plug that in, what I see is that this is proportional to the sum over the final states of the field of the square of the amplitude of the final states E plus at t times the initial state squared. Okay? So the whole thing, after all is said and done, is really about this. When I see this photoelectron, it's associated with absorption of a photon. And absorption of a photon is annihilation of the photon. Annihilation photons are from the positive frequency component, right? Everyone remembers that. So when I rewrite this as that times its star, then I take the conjugate, I sum over the final states of the field, and I have the initial states of the field, and then I have the conjugate of E plus is E minus. So I just wrote this times its complex conjugate, right? And since I'm summing over all final states of the field, this is a complete set, and so that's the identity. And so the bottom line of this is that the rate of absorption for or say the rate of a single photoelectron emission is proportional to that. Right? Everyone see that? Which is and it doesn't have to be a pure state. The initial state of the field could have been a mixed state. I'll just generally write that as the expected value of the intensity operator. The intensity operator now is, instead of E star E, what is the intensity is E minus times E plus. That's the intensity operator. Now, with the right units, it's intensity. Everyone clear on that? If I made this classical amplitudes, that would be what we had before in the semi-classical model, okay? But now we have the fully quantum model, and all that's changed when we did this for the case of single photoelectron emission is that we have to put in here that this is the intensity operator rather than that, okay? So, very good. And, you know, in particular, if the state of the system, the input state of the field, is a coherent state, I'm writing that coherent state as having its eigenvalue, the complex amplitude, okay? That is to say, E tilde of t is, you know, related to all the modes there's all the modes in this case, so that when I look at the positive frequency component acting on this, I get the eigenvalue back. So this is just a more sophisticated version of saying when the annihilation operator acts on alpha, I get alpha times the state back, okay? So that's what this is saying. So if this were a coherent state, well, this would give me back the semi-classical model, as expected. So if I have a coherent state, then the rate of absorption is proportional to the intensity, which is what we had classically. So as expected, if I have a coherent state, I get back the semi-classical result because the coherent state is the quantum state that gives me back the classical results. For this very reason, that is an eigenstate of E plus. And if I have a mixed state, which is a statistical mixture of coherent states with a positive definite Glauber P representation. So this then tells me that the rate of absorption is proportional to this. Because if I take the expected value of this operator, of the density operator with this, right? This is equal to the trace of rho with I hat. If I take the trace of rho with I hat, I get this. Is everyone clear on that? Why? Right? I take the expected value. And so, all of this saying that the quantum description of this is completely consistent with the classical theory. You recover the classical theory when the state is what we call classical light. But it does more. It also takes and allows us to think about interference of non-classical light, like a single photon state. So let's do that. Yes?
So for the rate of absorption, do you have to sum over all the intensities, like the average intensities of every single state? Because you just wrote that.
I said there's some particular input state that we started the field in some input state and we want to measure it. The way we do that is we shine this on this thing, and in this detector, there's some atom that's going to be photoionized. There's one particular atom that causes a cascade that will also ultimately detect as my photoelectron, the one that's been emitted. Okay? Hold on one moment. So the situation here is that I want to measure this field. So there's some input state of the field. It could be a pure state. It could be a mixed state. What we said here is, and I did this in the context of a pure state, that the rate of absorption was associated with the square of the matrix element going from the ground state of the atom to the excited state that gets radiated, where there's some initial state that is fixed. But the rate of absorption is independent. I'm never gonna, because I'm only measuring the electron, I'm not measuring the final state of the field. I have to sum over all possible states of the final field consistent with this. And that gave us this, okay? So I just wanted to first re-emphasize that. Now I want to understand your question about averaging over what?
I guess I was confused since you dropped the summation from, or do you mean to have the?
No, the summation's here, but what I did with a fell of a swoop is that I said this was the identity.
I see. Okay.
So that's how this came out. The sum went away because I'm summing over all possible states that are considered that because my measurement doesn't actually measure the field, it measures the electron. So I have to trace out the field.
I see.
Yeah. Yes?
When we constructed our interaction Hamiltonian, am I only concerning myself with stimulated emissions here? Is that because of the argument of
No, I want to go back, rewind. We talked for half a semester about Rabi oscillations, and we were very clear that that's not, we are drilled in our head, and we have to drill out of our heads that it's all about stimulated, about rate equations. This is not a rate equation generally. Generally, this is the coherent interaction, right, that gives us generally a Rabi driving. So we're not thinking about necessarily stimulated emission or stimulated absorption. We're saying this is the coherent interaction of the dipole with the field. And now, it is true when I start thinking about Fermi's golden rule, well then the whole story about Rabi flopping kind of goes out the door because I have the continuum of modes here. I don't have a well-defined state. And then I lose my coherence, and then really it is rates. And this becomes now a rate equation rather than a Rabi oscillation. But the main point I want to emphasize is that the Hamiltonian is a coherent coupling of the atom to the field. The only thing we've done two approximations. We made the dipole approximation, and we made the rotating wave approximation. So, I'm not sure, the point I really wanted to emphasize here is Fermi's golden rule tells us how to calculate the rate of absorption depending on emission. I shouldn't really think about this as stimulated emission or stimulated, it's just the absorption.
Thank you.
Okay, good. So, excellent. So now I wanted to go back and say, let's understand this from the point of view of interference photon by photon, okay? And in particular, let's think firstly about a single photon wave packet interfering with itself. The Glauber theory for photo detection here with the intensity operator doesn't require the state to be a coherent state or statistical mixture of coherent states. It could be any quantum state, including a single photon state, okay? Now, I want to come back to a point that I sloughed over in the past, having to do with the notion of a mode and the quantization volume, which we imposed in two different ways. We thought about the mode when we had something like a Fabry-Perot cavity, where we have some mode, and there's a well-defined mode in there. It has a volume. There's the distance between the cavity length, there's the cross-sectional area of the beam, and that defines kind of a mode volume, and we can think about the photon in that volume in the way that we've done. And in that case, we thought about the energy, and we said the energy density is h bar omega over the volume, and we use that to define the strength of the electric field. But when I'm thinking about this kind of picture, where I have a beam and I have a detector maybe coming out of the port of an interferometer or anything, and I want to talk about counting photons, what's my mode that I'm talking about? There's a spatial mode, there's a transverse area, but the length is, how should I define that? And the point here is that really what we're measuring here not is energy, but we're measuring is power. We're measuring the rate at which energy is being impinging upon us. So we really want to think about what are sometimes called temporal modes. One way to think about a temporal mode is to say, I'm thinking about now a kind of a tiny slice of this beam, okay? It has some transverse area which is associated with what we call the spatial mode of the beam. For those of you who speak that language, TEM00, okay? It's the Gaussian mode of that gives an area. It's the square of the radius of thing, okay? But I'm going to define some time delta t here, or c times delta t, which is the length of that, which is the time scale over which I'm going to measure. And that, in some sense, I can think about a quantization volume, in this case, like that. The area times that length, which is, I can think about that as the kind of quantization. So there's some notion, but what defines delta t? What defines delta t is the time scale over which I measure. My detector has a response time over which it integrates and then says click, and that determines the time over which I'm going to count a photon. And back in the retarded time, it's everything that was in that slice that I integrated that became. So that's what we would call a temporal mode, okay? Well, this is the volume of that temporal mode. I'm saying this slice, as opposed to this whole thing in the cavity, is the mode of the cavity. This is a temporal mode. The temporal mode has a duration delta t, okay? But if I want to think about various different kinds of delta t, I want to think about the mode per unit time. I want to think about the rate at which I'm counting photons rather than the number of photons. When I integrate that rate over a given delta t, I get the photons that are in that, okay? So we often want to take the limit as delta t goes to 0. And then I would have something per unit delta t, I'd have a kind of density that I could integrate over a given time interval. So we can do that. I can think about quantization per time interval. Okay. In which case, what I want to say is that if I think about the rate, well, what I want to say is the following. I'm going to define E plus of t here now in the following way. Notice that I don't have the delta t in here. The volume should have been C times A times delta t. But I've absorbed that delta t in A, so A has the units of 1 over the square root of time. Okay? So that A dagger A is no longer n, but it's n per unit time. I'll call this n dot. So that when I'm thinking about the temporal modes, I'm not thinking about the number of photons in a given volume. I'm thinking about the rate at which the photons are hitting my detector. So this is my rate at which photons are coming into my detector of length A. The expectation value of this is the rate rather than the number. Okay? Yeah?
So we're looking at the flux through that volume?
That's the flux. It's the flux. So when we don't have a fixed delta t or fixed time, it's more natural to think about it per unit time, and then I can just integrate this over any time. Okay? These, in different time intervals, these different modes commute with one another in the same way that A at k and A at k, the different modes associated with different wave vectors commuted. We have this same thing here, where we would say A dagger at t and A at t prime is now a Dirac. This is the continuum time equivalent of what we said when we had discrete modes. The creation-annihilation operator associated with different modes commute. Here they commute if they're at any infinitesimal time different, and when they're on top of one another, they are at Dirac delta. Okay? What are the units of a delta function? 1 over its argument. So this has the units of 1 over time, which is correct. This has the units of 1 over the square root of time. This has the, so that's how this works. Okay? So now I can think about a photon wave packet. Let's say the wave packet has some shape, 5t, okay? So that this squared times delta t equals the probability of finding a photon in time t to t plus delta t. Okay? In the same way that you think about in wave packets, psi of x squared dx is the probability of finding the electron between x and x plus dx. Okay, so psi phi of t squared is the probability density in time. Meaning I'm sitting at the detector, and I detect for some amount of time, this tells me the probability. If I integrated this over some time between 0 and t, this is the probability to find it between 0 and t. Mm-hmm.
Would it be incorrect to just call that a wave function?
It is.
It is a wave
It is the wave function. So this is the wave function of the photon. Okay.
It has units 1/root times.
It does.
Root space.
It's exactly. Instead of as we typically do root space. But now I'm fixed here, it's coming at me. Because everything's moving at the speed of light, I can turn space into time and see. Beautiful. So, now I want to talk about an operator that creates a photon in one wave packet. So that, as we talked about in second quantization, is this. So when I act this on the vacuum, I have created one photon in that wave packet. Okay. So this state is a single photon state. This has one photon, and it's not just one photon, it's one photon with this wave function. Okay? So now I want to go back to our Mach-Zehnder interferometer. And I want to say, I have a detector, and I want to know what is the probability of finding a photon at this output port? Or said another way, what's the rate at which I expect to see? If I wanted to find the probability, I integrate that over some time. What is the rate at which I would see that? Maybe I'll do the probability. So the probability of seeing this photon in some time interval between 0 and t is equal to some constant, is proportional to some constant. What we just said from the Glauber theory was this. So this is the output intensity. That's what the Glauber theory tells me. The Glauber theory tells me I need to look at the intensity, and that gives me the rate at which photons are being absorbed or counted. Now I'm going to integrate over some time between 0 and t. Let's be generous. Let's say we're going to integrate over all times. So then I'm just going to say, let's probably include that. All right. So this thing over here is equal to, this constant out from h bar blah 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 ca times the integral 0 to t a dagger out at t a out of t. using our quantization that we had over there. This is just what I called n dot at the output port. Okay. All right. So what is this output annihilation operator? Well, we solved that using homework 7, week 8. I don't remember where we did the whole story about the scattering and the beam splitters and the like. And the amplitudes of the classical field transform the same way as the annihilation operators. And so what is true here is that A out at t is equal to 1/2 A in at t minus 1 plus A, or A dagger, doesn't really matter, just like we had here. Yeah, we need a half.
Second.
This is multiplying both of them.
Oh.
There's a parenthesis. Yes. Okay. So, just as before, the classical amplitudes transform that way. The quantum annihilation operators transform this way. Okay. So, when we put this all together, this thing is equal to n in dot t minus t1 plus n in dot t minus 2 plus twice the real part of A in dagger t minus t1, A in t minus 2. All I did here is just I substituted this as A dagger A and multiplied out the 4 terms, give us this. So what I see is almost exactly the same thing that I saw over here. I had the sum of the 2 intensities associated with the 2 possibilities. Either the photons came at a time delay t1 if they took path 1, there's some rate at which if they took path 2, and there's an interference term. Okay. So let us now calculate these guys. Okay, so this is my number rate operator. It's A dagger A. Okay, and I want to calculate that expectation value for the specific input state that I had a 1 photon wave packet. I created 1 photon with that wave function. That's what I did. Right? And I want to calculate this expectation value. Now, this is the dagger of this. So I can write this equivalently as that. Does everyone see that? It's the norm of that work. So we need to calculate the norm of this. Let's plug it in. Let's take this input state and let's plug it in. And what I get is this annihilation operator acting on A dagger of phi acting on the vacuum squared. You with me? How are you going to calculate that? Anyone have an idea? Take a look at this guy. Yes, Nate. The commutator. Thank you very much. Most excellent. if you always, when you wanna move this to the left, I mean, excuse me, I'm dyslexic, to the right, and so this annihilates, and then what's left is the other way around. So this is equal to its commutator. Right, everyone see that? Because you're right in the other direction. That's a trick of the trade that everyone needs to see how that works. All right, so let's calculate this commutator. This guy equals the integral from minus infinity to infinity of the commutator of t minus t1 with so what I did is I plugged in, where the heck did it go? Where is that? Oh yeah, thank you. I plugged in this, okay? But this is a dummy variable. Since I've used t, I just call that t prime, okay? What is this commutator?
Direct delta.
A Dirac delta. This is Dirac delta, t prime minus t minus t1. All right, I said t1, there, but t prime. Okay? And so what is this integral? Okay? And similarly for this guy. Okay? Now this guy's a little bit more tricky, but it's the same thing. I have to do these commutators. And so the bottom line I get is that the rate of photon detection is proportional to the integral from 0 to, or from minus infinity to infinity, dt. The first term is that. The second term is that. Each one of these guys, remember I did the square of the amplitude. And then the third term over there is equal to the real part and so let's be, if these guys are each normalized, if I integrate over all things, that's 1. So I get a quarter plus a quarter is a half times 1 plus the real part yes.
How should I think of that term? The real part of phi star phi. Should I think of that as the wave packet interfering with itself at length?
I should. It's exactly what I should think about.
It's like here,
It is exactly this.
The autocorrelation function.
We're looking at the wave, in the classical wave theory, we saw the how much intensity came out here was related to looking at the wave amplitude with itself at 2 different times, those 2 different times determined by the time difference between those 2 paths. I mean, it literally is t minus t1 and t minus t2, but I use the fact that this thing was stationary to turn that into that. In this case, it's exactly the same thing. But now, instead of thinking about the electric field, it's the wave function amplitude. Yes, Nate?
If we integrate over,
Oh, yes, you're absolutely right. Excuse me, we should integrate this over all times. Thank you. Yes?
Is there a characteristic coherence time?
Yes, so that's an interesting question. So, if this was a single photon wave packet, let's say it was a Gaussian wave packet in time. So, it comes by me, it's got some width, let me call that width tau c. And I put this single photon wave packet on this interferometer. Over what path length would I expect to see interference? Interference meaning that sometimes I get constructive interference, sometimes I get more than a half, and sometimes I get less than a half. If this term were 0, we would say half of the time the photon comes out there. Because this is actually the probability. This is the probability of seeing that photon, which I can, okay, come back to this. So I want to answer Benny's question. So, and I want everyone to answer this question. For this particular problem, what is the path length difference or the time difference such that I would expect to see interference?
It has to be.
I'm listening. I won't look, listen, I'm listening. For this particular single photon wave packet, which has a width I'll call tau c. I have to be within tau c. Because otherwise, at one path that comes out, there's an amplitude for it to come out here, and there's another amplitude to come out here, and they don't overlap. It's only when they overlap. Okay? So the coherence, and that would be the same as the coherence time of a coherent pulse. If I had a pulse, a coherent pulse, a classical light that was a single pulse, wasn't a pulse train, wasn't a mode lock laser, which is a Q switch laser that shoved out one giant pulse. If the pulse has a femtosecond width, if the difference between these is bigger than a femtosecond, I'm not going to see interference. But I can think about that as photon by photon. So classically, some fraction of the amplitude comes out here, some fraction of the amplitude comes out here all the time. Quantumly, the photon either comes out here or there, but I don't know which one, and the fraction of the time it comes out here or the fraction of the time it comes out here is related to the probability of it being here or here, which is exactly the classical solution. So we just saw, just very formally, with super duper fancy second quantization and 8 aggregates of wave packets and God knows what other piece of math I threw at you, the story of how you see formally the photon interfering with itself in a single photon wave packet. Okay. But what if I had what about a coherent state? How do I think about that for a coherent state? How is it any different?
Well, if it was a coherent state, could you really think photon by photon?
It's the same thing, but photon by photon. Each photon, the coherent state doesn't have a definite number of photons. It has an uncertain number of photons, but no matter how many photons there might be, each photon is doing this. Okay? Oh, sorry. And so we can see that, but in a very formal way. Okay? So let's say I have a coherent state. My coherent state is going to have some associated with some amplitude. Okay? I'm going to say that amplitude is the square root of 2 pi h bar omega over AC in my temporal mode times some complex amplitude such that this is the mean photon rate. Remember, when we had volume condensation, we said this was the number in that volume. Now this is not the number, it's the number per unit time, okay? So my coherent state in this case is equal to the displacement operator, which I'll say is characterized by this wave. Now I have to integrate over all time, alpha a dagger minus alpha star a dt. Acting on the vacuum. So this is my displacement operator. I'm sorry. This is my displacement operator. And my coherent state is the displacement operator acting on the vacuum. Okay? So what's fancier than what we wrote before, this is a multi-mode. I can think about this, remember we had this here. I can break this up into different modes. Is that clear what this is, right? So this operator is such that if I write this, acting on this, I get the amplitude back. But if I look a little bit more closely at this guy, let's think about this. As, oh, sorry, maybe I'll write it this way. If I look at the mean of the intensity operator, then, is proportional to n dot is A of t dagger A of t. If I have a coherent state, and I plug this in, I get that. Okay? So it's just as before, this is the intensity, as we expect classically. But how do I think about this as photon by photon? If I look at this operator, well, this looks kind of similar to this. The difference now is that alpha is not normalized to be 1, it's normalized such that if I integrate this over all times, this is the mean number of photons in the field. So if I divide it, I can write this as, I can define phi of t as the square root of the mean number of photons. I can define alpha of t as the square root of the mean number of photons, phi of t. So this is n bar. So that is to say, the displacement operator is n bar a dagger of phi minus n bar a of phi. So, what am I trying to say here? What I'm trying to say is if I look now at the coherent state,
Yeah, memorize that.
thank you, good job. But the point I want to make is my coherent state might be a pulse. My Q-switch laser that puts out a pulse that has a certain shape. what that pulse is a collection of many photons. It might have 0 photons, it might have 1 photon, it might have 2 photons. It has a Poisson distribution depending on its mean photon number. But every photon is in the same wave packet. I don't know how many photons there are, but every photon is in the same wave packet. And that wave packet is just determined by the pulse shape, which is given by various normalizations, what I call alpha. And it's just, I've created n photons in that wave packet. When I send this through the interferometer, every one of those photons does what we just described over here. Every photon interferes with itself, and at the end of the day, there's an amplitude for it to come out here or here, and this tells me the probability. And every single one will do this. So as Dirac correctly said, in the classical wave, when I'm looking at an interferometer, I'm looking at the detection of a single photon, I should understand that not as some collection of many photons interfering with each other, but as each photon only interfering with itself. The fraction of them that come out, one way or the other, is determined by this expression, but I only have to think about it as photon by photon. There's no multi-photon effect, okay? But that's because our detector was only counting photon by photon. If I come back to, well, I guess it's gone now. Or is it? Yeah, it's gone. Temporary ground and twist. There we have 2 photons, because we have 2. So we have to, it's not the same problem. And so we'll resolve this paradox finally in the next lecture. We'll now understand, we want to go back and now think about the Hamburg-Brown twist experiment and how we can, we've explained the Hamburg-Brown twist experiment in terms of waves. We've explained the Hamburg-Brown twist experiment in terms of fluctuating waves, and that there was a high fluctuation when the time was 0. There was no correlation when time was bigger than the correlation, and we saw that fall off. So that was a wave. How do we understand it from the point of view of particles? What's happening to photons? What's interfering with itself in the case of the Hamburg-Brown twist experiment? Yeah?
Does it have to do anything with identical particles? Meaning if I did it to photon, I don't know which one is it, it evolves.
Absolutely. So, as we were saying, there are two different ways I can see a coincidence count. If these are identical particles, I can't tell whether this process happened or that process happened. And so I must add the probability amplitudes. What interferes, this is what's called 2-photon interference. As opposed to the 1-photon interference. And what is interfering with itself are these 2 histories. When you have one particle, its history is what path did it take? Did it go that way or did it go that way? Those are the 2 histories that can lead to a detection. So we talk, and when we think about a single particle interference, we always talk about interference between 2 different paths. But the more general statement of it is the interference of histories. What 2 histories or processes that cannot be distinguished by anything in the universe? There's nothing in the universe that tell us whether this happened or that. What Feynman taught us is that we must add the probability amplitudes associated with those 2 histories and then square that amplitude to get the probability of the event. And the event is coincidence, is that both of these detectors went click. Okay, so we'll follow that up and complete this story next time. Yay! Woo! It's a tough one.
He's finally excited.
Trying hard. Have a good afternoon, everybody.
Thank you.
I think,